Hello viewers, welcome back to another section of my multivariable calculus tutorials. In this video, we're still going to solve problem in surface area of quadric surfaces. Yes, we've solved many examples in our previous tutorial, so if this is your first time visiting this channel, don't forget to subscribe so that you get access to all our videos. And let's see what you have in this video. Don't forget to watch the video to the end and share as well. Determine the surface area of the hyperbolic paraboloid fxy, which is equal to 9 plus x squared plus y squared over the disk r, which is a function of xy, that is x squared plus y squared, which is greater than or equal to 0 and less than or equal to 4, right? So this is surface area, but the surface given and the region given will be able to compute this in the using the polar coordinates, right? Yes, you can't use the Cartesian to compute this. So this is an application of the polar coordinates to compute the surface area of a parabolic or of a quadric surface. So let's see how we're going to do that. So first of all, you know that the general formula for finding the surface area S is equal to the double integral of square root of fx squared plus fy squared plus 1 dA, right? Yes, so what we need now is to find this expression. So what is our fx? From our parabolic or from our paraboloid, we have the equation fxy to be equal to 9 plus x squared plus y squared. So our fx will be 2x and our fy will also be 2y. That is the partial derivative with respect to x and y respectively. So I'll get square root of 2x all squared 2y all squared plus 1, and this is going to give me 4x squared plus 4y squared plus 1, right? So once I get this, I drop here. Now I need my limit for my integration, but I was given a disk. And what is a disk here? The equation of the disk given was x squared plus y squared greater than or equal to 0 and less than or equal to 4. And this is a perfect circle, right? Yes, it's a circle, equation of a circle. So the circle has boundary from 0 to what? 4, right? Yeah, so meaning we have to convert this to the polar coordinates. And the polar coordinates, we are interested in two parameters. We need our theta and we need what? Our r. R is the radius of the circle and theta is the angle that radius makes with the xy plane. So at this point, you know x squared plus y squared gives us what? R squared, right? So from here we can see 0 is less than or equal to r squared, less than or equal to 4. Hence our radius will be from 0 to what? To 2. So 0 less than or equal to r, less than or equal to 2. So this becomes our boundary for our radius. Since it's a disk and it's a complete disk, we're going to have the theta to be greater than or equal to 0, less than or equal to 2 pi. We have our limits converted into our polar coordinates. Then finally we come to the function. We convert this function to the polar coordinates, right? So if you have the square root of 4x squared plus 4y squared plus 1 to the polar coordinates, what you're going to do is you're going to factor out 4 out x squared plus y squared plus 1. And you know x squared plus y squared is r squared, right? So we're going to get root of 4r squared plus 1. Then I bring my integral back again. So in the polar coordinate, you write double integral from 0 to 2 pi. The theta takes the external, then the r take the inner. So 0 to 2 for the r, then the square root of 4r squared plus 1. Then you introduce r, the theta. So your dA is r, the theta, right? So when I get something like this, the next thing I'm going to do is I'm going to compute this simple integration here. So this will be a substitution. So let u is equal to 4r squared plus 1. Our du over dr is simply equal to 8r. Therefore my dr is simply 1 over 8r du. I bring everything back here. Integral 0 to 2 pi, 0 to 2, root of u multiplying my r here, then multiplying 1 over 8r du, right? This r simply cancel this r, and I'm going to have one integration to be integral 0 to 2 pi integral 0 to 2 u to the power half over 8 du, which simply goes to 0 to pi. Then I'll have 2 over 3 multiplying my 1 over 8, then u to the power 3 over 2. This is the simple integration I have here from 0 to 2 d theta. Then at this point, 2 go into itself 1 and go here 4. So I'll get 0 to 2 pi, then 1 over 12 e to the power 3 on 2 from 0 to 2 d theta. So what is u? U was 4r squared plus 1, right? So integral 0 to 2 pi 1 out of 12 4r squared plus 1 to the power 3 over 2 0 to 2 d theta. And just to simplify this, so if you have this integral 0 to 2 pi 1 over 12, wherever I see r, I'll put 2 there. Here when I put 2 there, I'm going to get what? 4. So 16, that is 17, 3 out of 2, right? Yes. Then minus 1 out of 12. When I put 0, everything will vanish. So 1 out of 12 becomes 1 out of 12, like this. Then everything d theta. Right. So once I have this, the next thing I'm going to do is I'm going to integrate this whole thing with respect to theta. So I'll have integral 1 out of 12 17 to the power 3 over 2 minus 1 out of 12 theta from 0 to what? 2 pi. So with this, we can put 0, when you put 0, everything will be 0, so we are interested in the upper limit. So our solution is simply 1 out of 12, open bracket 17 to the power 3 over 2 minus 1, multiplying what? 2 pi, right? So my pi, 2 will go and cancel this 12, so that gets pi on 6, multiplying 17 to the power 3 over 2 minus 1. You can leave it like this, or you can still further simplify. This is the end of our video and the end for this section. See you in the next section. Don't forget to like, subscribe and share.